If you're new to the blockchain space, then it can be a little intimidating trying to grapple with all the complexity and new terminology, but I'm here to tell you that it's not as complicated as it might seem. Hello, my name is Trent Fowler and I'm a machine learning engineer, public speaker, and cryptocurrency analyst. This channel is the home of the Futurati podcast, where we dive into how emerging technologies will impact the world and your bank account. So if that sounds good to you, hit that subscribe button to stay up to date. In this video, we're going to talk about blocks, what they are, how they're made, and how they're chained together to produce this thing called the blockchain. But first, I want to start with an analogy. Imagine you had a magical book from the library at Hogwarts where everyone with a copy can instantly see when any new entries are made. If someone goes back to page 1 in their copy and makes a change, their book turns bright red so that every single other person knows that a change has been made and that the record is compromised. Forget about blockchain for a moment and just think about these books and their immutable record. Can't you imagine things it would be useful for? If you needed to store really important information that you didn't trust one person to manage alone, like financial or medical data, having a magical book to record it in would clearly be great. Well, the analogy between blockchain and magical books certainly isn't perfect, but it'll help more than you might think. So let's get into blocks. On the blockchain, blocks are just clusters of transactions. Special members of the Bitcoin network called miners will gather the transactions together, form them into a block, and then mine them, which is putting the block on the blockchain and making it part of the distributed ledger. Transactions are validated in a two-step process. Step 1 is verification, which is when nodes in the network check a transaction against a long list of criteria to ensure that everything is in order. Step 2 is confirmation, which is mining a block containing the transaction. Let's talk more about step 1, verification. Remember that Bitcoin is a peer-to-peer network. When I perform a transaction, I tell my friends on the network about it, and they verify it by checking to make sure it meets all the criteria on the list. There's something like 15 or so checks that need to be performed. Some of them are pretty complicated and have to do with the size of the transaction and how big a block can be. And some of them are relatively straightforward and include things like checking that the inputs haven't been spent anywhere else already. Once a transaction is verified, it's added to the mempool. Mempool stands for memory pool, and it's just a set of transactions the network knows about, but which aren't actually in a block yet. Miners will begin pulling transactions from the mempool and forming them into blocks. Blocks consist of two parts, the transactions and the header. The header contains important information we need to understand. There's a fair bit of data in the header, but all of it falls into three big categories: competitiveness data, summary data, and reference data. Let's discuss each of these in more detail. The first category is competitiveness data. This consists of something called the target, which tells you how hard it is to actually mine a block, the timestamp, which is when the block was created, and the nonce, which is an integer counter that plays an important role in mining. We'll have more to say about the nonce in the next video. Let's talk more about the first kind of competitiveness data, the target. The target is the proof of work algorithm's difficulty requirements. So in essence, what this does is specify how hard a miner has to work in order to create a block that is acceptable to the rest of the network. You can think of this as basically being a knob you can turn up and down to make it more or less difficult to mine a new block. The example that's sometimes used is to compare mining to solving a Sudoku puzzle. A 3x3 Sudoku puzzle is much easier to solve than a 13x13 one. You may be wondering what the purpose of this is. Well, what the blockchain wants is for a block to be mined roughly every 10 minutes, give or take. So the network metaphorically increases the size of the Sudoku puzzle as more computers try to mine blocks, and decreases the size of the Sudoku puzzle if computers stop trying to mine blocks. In other words, Bitcoin adapts to the world's attempts to mine new coins. If we all throw everything we have at it, then mining becomes more difficult. But if we back off, mining becomes easier. The net effect of these adjustments is to have a new block mined, on average, once every 10 minutes. So that's the first category, competitiveness data. The second category is summary data. The summary data is composed of a Merkle Tree root, which cryptographically summarizes all the transactions in a block. What creating the Merkle Tree root involves is rolling all the transactions up into a single hash value that summarizes all of them. Hashing something, whether it's a single transaction or it's the entire block header, means feeding it into the SHA-256 hashing function. There's nothing scary about that. It's just an algorithm which takes an input with any length and produces a long string of letters and numbers. the output of the SHA-256 algorithm has a few important properties. It's always the same length, no matter how long the input is. The same input always generates the same output. So if I put in a lowercase a 50 times in a row, I always get the same output string. Changing the input changes the output in ways that cannot be predicted in advance. The Merkle Tree algorithm first hashes transactions, then hashes pairs of transactions, then hashes pairs of those hashes until it has a single hash which uniquely stands for all the transactions in the block, as though it's climbing up a pyramid to a single point at the top. It will always be exactly the same for a given set of transactions, and changing any one transaction by even a small amount will completely change the Merkle Tree root. So at this point, we've talked about the first category of header data, which relates to competitiveness, and the second category, which contains summary data. The third category is reference data, which is a pointer to the previous block's hash. Where does that come from? Well, after we've hashed all the transactions to create the summary data, the last thing to be hashed is the entire header, the timestamp, that little integer counter called the nonce, the Merkle Tree root, everything. Each block contains the hash from the previous block's header, going all the way back in an unbroken line to the very first block. That means we have a series of blocks which are chained together through references to each other. And we call the system a blockchain. To recap, some miners wanting to get the Bitcoin reward pull verified transactions from the mempool, pile them up into a container, and make a header for it. The header has the timestamp, the nonce, the Merkle Tree root, a reference to the previous block's hash, and everything else discussed so far. A hash is created for the whole header during the mining process, and the next block will contain a reference to this block's hash. Now let's pause for a moment and consider what we've covered. We know that hashing a given input always produces the same output, and if you change the input, the output changes dramatically. We know that all the transactions in a block are cryptographically summarized by a Merkle tree. We know that a block's header is hashed, and we know that each block has a reference to the previous block's hash. What happens if I go 5,000 blocks back and I change one transaction to give myself more money? The hash of that transaction changes. That change cascades up through the Merkle tree so that now the Merkle tree root for that block is totally different. The hash for that block header is now also totally different. And the hash for the next 5,000 blocks, each of which contains a reference to the previous block's hash, are all totally different. So it would immediately become obvious that my copy of the blockchain is different from everyone else's, and they would reject it. That's it for this video on blockchain blocks. I hope you found it enlightening. Don't forget to like it and subscribe to our YouTube channel, or check out some episodes of the Futurati podcast where we talk about everything from crypto to AI to quantum computing to space exploration. And you can also follow me on Twitter at Trent_stempunk. Thank you.